Okay, so this is a 1975, 1976 Videomaster Olympic video game console for the home. And perhaps you can see, I've got it open here, but you may recognize that console. There you go. Videomaster Olympic. Bought this relatively affordably. I want to play Pong, which is what this plays, and a few other games that look a lot like Pong. What's really amazing about this circuit is not only is it through-hole components, it's 1975 design, but also there's no software in this at all. It's entirely logic-driven. These black ICs that you see, they're just examples of the 7400 and the 7402. So they're NAND gate and NOR gate chips. They're these two things here. So every 3 pins on these devices, you're getting an isolated, independent logic chip. Either it's a NOR or an AND. I'm sorry, NAND. So in theory, this is a pretty straightforward, beautifully logic circuit. And what's captivating for me is, number one, does it work and can I repair it? If not, because all the components should be replaceable. These are still made as basic chips, and resistors and capacitors, and that's it. Potentiometers. The magic is, how does this thing actually construct an image that can be displayed on an old TV? Over here we have the RF modulator, which would take the video signal, the composite video signal, and send it out into the back of the TV. But before it gets into the RF modulator, we should be able to see it at pin C over here, before it then gets upscaled to UHF, about 900 megahertz or something. And so I've got a battery on, and we're going to switch it on, and we're going to take a look at what the output is on the scope. I suppose we're looking for a video signal, so if I get this here, we've got nothing. Okay, so I'm just going to switch it on underneath. Click. Let's go and sample the video signal. And there we have it. We have something. You can see the sync pulse, line frame sync pulse, and a little bit of a blip. And I kind of would expect a bit more stuff on that video signal. It just suggests there's like a white, I don't know, a white line on the right-hand side of the screen. If you imagine what this thing might look like. Anyway, gonna have a poke around with this and see what we can see. Challenge is I don't actually have a old TV with an analog decoder for these video signals, composite video signals. So I'm going to try to build an adapter so that I can display it on the old analog scope. Well, it's not so old, although it's a relatively last of its type, a couple years old. We're going to see if we can get this output, whatever it looks like, to display on that scope, and then try to debug this and make it go. Yeah, there's a couple of test points in here where I think you should get saw wave voltages or ramp voltages, but I don't get anything. At the moment, it's pretty much flat. Yeah. Let's see. All right, back to this Videomaster Olympic console. I don't have a way of looking at the display to kind of plug it in to see if it works. Not yet. But looking at the schematics, and this is from the VM3 kit. This is the same circuit in a slightly more modern box style. This is the Videomaster Olympic 2, and it's called the VM3 Mark II. The Mark II, I think, was more cosmetic, but functionally, this is what's in this box. The schematic talks about gates, so chip N1, N2, and gates 2, gate 3, gate 4, G5, and so on. It doesn't tell you what the pins are, and so I've spent a bit of time kind of reverse engineering what pin 1 and 2 are, pin 12, 13, and so on. And I've just been using a continuity tester to do that. kind of testing the pins and so on. And sort of just seeing if I can actually get the core signals coming out. The bat left signal, the center line signal, the bat right signal, and the line sync signal coming out of the first part of this chip. And, you know, as part of the kit, believe it or not, this was the earlier version of this. The Mark I was sold as a kit in 1975 for about 25 pounds. You could buy the built console for about 40 pounds. That's 50-year-old money. But if you built the kit, you had the construction manual. And here we have it here. The Videomaster kit, home kit, blah, blah, blah. And the kit tells you all about the circuit function, how it works, and behaviors within the circuit. And first thing to do, after you're talking about the power supply, looking at the line frequency pulse generation, typical waveforms of a line frequency pulse generator. So those 4 outputs being generated by the logic circuits here. So the bat left, center line, bat right, and line sync should look like this. And indeed, that's what I'm seeing. So you can see you've got the line sync pulse, then you have a bat left dip. There's your line sync pulse, there's your bat left dip. And then when that dip ends, the center line takes over for a little bit. And you can see that as this dip ends, the center line dip takes over. And then at the very end, when that center line goes away, the right bat takes over and lines up with the sync again. And you can see that here. The bat here takes over, and then that stops, and you go back to this dip here on the top line. So that's excellent. And yeah, it gives a recommendation of 64 microseconds if the horizontal control is tuned so that the whole circuit's operating around 15.625 hertz. And indeed, if I tweak the horizontal control dial here, and basically what that does, I'll show you briefly in a second. But if you measure it out to about 15.625-ish, 64 microsecond gap, things line up. And that looks pretty amazing. When you play with the horizontal control, you just turn its potentiometer. You'll see that the scan shifts a little bit, but actually the ratio, you can see this, it's getting narrower, everything's getting narrower, and if you widen it, everything's getting a bit longer and wider. So we've passed the first hurdle. It's definitely doing something. I checked the power consumption. It's about 15 milliamps, sorry, which is right in the range of 10 to 30 as specified as well. So yeah, we're piecemealing our way through. Next thing is to check on frame frequency. So this is the line sync signal. So this is the information that would allow you to raster the lines across the screen. Now I want to look for the frame sync signals, which is off another part of the circuit, gates 6 to 9, which is, where is gate 6 to 9? Down here, which I've also worked the pins out for. Cool. Okay, so just investigating, in the previous video we talked about the free-running oscillator, which is generating the left bat, center line, the right bat, and the frames, the line sync signals. And we saw this diagram, and that's working. But when it comes to the frame sync signals, which operates at a much lower 50 hertz rather than the line frequency of 15,000 for a 625 PAL lines, we would expect this similar kind of layout. And indeed, if you compare this, although this has 5 gates, if you ignore that first gate, you have this kind of cascading gates process where you have a variable potentiometer feeding an RC network into the as one input into each gate. There's an RC, and the output from the previous or the leading gate goes back in as the other input. The output from pin 8 here goes back to pin 13. The output from this gate goes back to here. Now that kind of cascading arrangement seems to oscillate and work well, and the relative duration of the low pulses is based on the RC network, C2, R2, or C3, R3, and so forth. So we take exactly the same approach here. We have a series of 4 gates with the RC networks. You can see the pair here, and the output of one gate goes back to the input, the other input of the previous gate. And this gate here at N3, pin 11, goes into the input of the previous gate, and so on. This should generate this output, where you get pulses of different durations, low pulse, low pulse, low pulse, and a sync, based on those RC networks. And yet what I get is essentially no pulses. So what you're looking at here is a high, a low, and a high, which is essentially what you would get if you look at the high signal, a high signal, a low signal, and a high signal. So if you kind of ignored these end bits where the pulse is rising and lowering edges, if you just look at these, high, high, low, high, that's what I've got. High, high, low, high. It's as if the frequency of this oscillator is like measured in days rather than 50 hertz. I don't know. So something needs to be looked at here. It should be relatively straightforward because, after all, it's just a couple of gates, a couple of RC networks. And we know that kind of arrangement works. So, All right, further investigation. Why am I not getting the frame sync pulses? As we said, I can get the line sync pulses correct, but this one is not the case. In fact, it seems like I'm stuck in the high, high, low, high status without any of these pulses. So you kind of ignore that and you ignore that. That's what I'll see on the scope. It's all coming from a single chip, which is this one here, N3. And the way it's set up, these are 4 NAND gates, and the NAND gate produces a high output. Okay, those outputs are high when these inputs are high, low, 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 high, whatever, a bit of a mix. The only way you'll get a pulse, which is the frame sync and the net height and so on, all these outputs, these 4 outputs, the only way you get a pulse is when both inputs on a gate are high. And what happens is when this is high and you get a high input here across this RC differentiator network, the behavior when you get a high input going into, imagine this gate here is producing a high square line pulse. It goes through a differentiator network like this. The voltage here, which is the input that we're looking for, so the input here going into this gate actually looks like this. It has a kind of a big spike, and then it decays. And this decay, exponential decay, is based on the size of the capacitor and the resistor. So when this input from the output of this gate goes high, we get an immediate spike. So instantaneously, both inputs are high, triggering a low output, which is what we're looking for. And that low output stays until the voltage here decays to the point where the threshold of the gate considers that the input is sufficiently low voltage to be considered a low input. That then has a high and a low input, and that changes the output to high again, so that we kind of finish the pulse. So the width of the pulse, the time spent where the output is low, is based on this voltage being instantaneously high to match the high pulse here, and then decaying lower and lower and lower through the charging activity of the capacitor and this resistor until we get to the threshold where the chip thinks it's the voltage is sufficiently, call it, low. Now, that makes perfect sense. So this first gate has a very small resistor, so the charge time is very quick, and so you get the smallest pulse. The next resistor is reasonably large, and you get a longer pulse. The third gate has a huge resistor, and so you get a very slow charge time, and you get a longest pulse. And then finally, this one at the end is not quite as big as the first, and so your pulse is a little bit shorter than that one. And of course, then it just cycles back. Then you start back with this one. This cascading, when you finish the first pulse and you have the rise time, that triggers the second pulse. When the second pulse is finished and it has its rise time, it triggers the third pulse, and so on, right to the end, when it goes back to the beginning. That's precisely because of the cascades. These outputs, when this pulse comes out from low back to high, that triggers a high pulse here, that pulls this value of voltage high, which then charges, and this one, and then this one. So you get this cascading effect. So why do I not get the pulses? All I get is this stuck behavior here, high, high, low, high. Well, the problem seems to be in this third gate. These outputs are high and high, and when this goes high, this voltage gets pulled up, and you get the spike. You get this initial spike that matches the square pulse, and then there's a decay. And I validated that on the oscilloscope. You definitely get that spike and the decay, but the output is always low. So it's as if you've had the spike, you had the two high inputs, you get a low output, you start this low pulse, but you never finish it. Because when the voltage goes low here, so you'd have a high-low, you'd expect this output of the NAND gate to go high, and it doesn't. Now, so I think this gate is broken, which means replacing this chip. I've tested the resistance values. One potential risk was that this capacitor would shorted. If it shorts, then the high voltage goes straight to the input pin, and it'll always stay low. But it seems that that is not shorted. It's producing the correct decay profile. It's just that at the input, when this is low and that is high, it stays low, and that's wrong. It should go high. And it doesn't go high, therefore we don't get the propagation of the pulse going to the next gate to close this one and start this one and then continue around. So we are stuck precisely where I thought, in these high, high, low, high stage, because this gate is never going back high, because irrespective, it's not looking at the inputs, it's still stuck at the low output. So I think I have to replace that chip, which is this one. As one last observation about chip N3, which I think is broken, it's exhibiting some strange behavior. If I measure one of the pins, like pin 1, you'll see that it's about 1.6 volts. And this 1.6 volts is the voltage which you can adjust through the vertical adjustment. So if I twist the pot one way, you get 0 volts basically, and if I twist it the other way, you get about 2.5 or something. Yeah, 2.6 volts. Okay. Now, so let's put it in the middle somewhere, and you get about 1 something, right? 1.5. And that is pin 1, which is down here. It's one of the inputs to a gate. But then something strange happens. If I measure that gate output, pin 3, with my logic probe, and I'll stick it on there. So now I'm measuring it on the scope somewhere. And I go back and measure pin 1, it's a completely different value, 5.6. 5.6 volts. So the act of measuring the gate output, one of the gate outputs, not even the suspected broken one, if I simply, so the voltage here is whatever it is, 0 to 2.5 volts, okay? And it's the same across all of these RC network inputs. But the act of measuring the gate output changes that input dramatically. Now, my probe has a 100,000 ohm impedance. It shouldn't weigh down a CMOS chip materially differently. In fact, I've tested it against the other known chip, that one up there, that one that's producing the line sync sockets. When you measure with a scope, you don't materially change the voltages here. So there's something funky going on in this chip that if you measure it, the act of measuring it changes the value at the input. Yeah, strange. And that's not even the gate that I was suspecting. This gate seems to be the one that's broken. So I think that's another piece in the puzzle to replace this chip. Well, so I have decided to take out that chip that doesn't work. And there it is, the MM74C00N quad NAND gate. And I replaced it with a socket to be able to put in some replacement parts. There we are. These are from 1982. It looks, looking at the date code. They don't make these chips anymore, and well, they don't make this particular type with the voltage rating that I need. And so the replacement parts are inevitably going to be new old stock. This is already, what, 41 years, and hopefully get a chance to use some good chips. This is why I'm using a socket. If you replace it with a new old part and it doesn't work, you're going to have to take it back out and then replace it with another socket and keep going. And the risk is that the PCB tracks on the back will be, you know, the victim of too much reheat and will eventually break, in which case you've got to replace the chip and then repair tracks. So, so I'm going to pop one of these replacement chips in and hopefully get the this frame sync pulse generator. Well, it's more than just the frame sync, but it's one of the pulse generators going. This is a significant chip because not only does it provide the frame sync, and also things like net height and the baseline and the top line and so forth of the image, but it also then goes in and creates ramp generators here and here, which were actually used higher up to actually shape the size of the ball and the width of the bats and all sorts of stuff. So a pretty incredible circuit as I work through it, but this is pretty fundamental to getting a lot of it working. And once we put it in, we'll test it and see if we get the expected, let's pull it over here, expected pulse sequence. And you'll notice the pulse sequence is contiguous cascade of pulses, so that the frame sync, when the rising edge starts, the second pulse starts. When this rising edge, this starts. When this rising edge starts, this, and back to the original. So it needs to be sequential pulses, compared with the line sync, which is working, where there isn't necessarily a sequential rising edge, falling edge pair. There is here, here, and here, but not here. There's a bit of a delay for various reasons, I guess. Anyway, okay, so the next clip you'll see is hopefully this image on the oscilloscope. Okay, so sampling the chip in the new chip, taking the outputs of this pin 6, 8, 11, and 3, we get life. And it looks pretty good. If I take a single shot just to kind of pause it, we get, what do we get? We get a quick dip of the frame sync. When that rises, we get the dip of the next line. When that rises, the dip of the longer line. And then finally, when that rises, we have a dip of the final line, the fourth channel here. And when that rises, we go back to the frame sync, which is exactly what we're aiming for. Now, it mentions the frequency is around 20 milliseconds. So let's measure that. And let's have a rough check here. I'm measuring just there 17.9 milliseconds. But what's interesting is if I remove the cursors, of course, this oscillation, the frequency is controlled by this potentiometer. And as you can see, if I turn the pot one way, You actually see it kind of syncing with the display on the scope. And if I go all the way to the left, the relative space, it gets a lot more tight. You know, if I take a single picture there, and let's have a cursor measurement, we are something like, let me make it a bit bigger. Oh, where's my first display? There it is. It's over here. Something like that. Something like that. 10.8 milliseconds. And if we let it run again, and I just tweak the pot as full to the left, if I tweak it all the way to the right, basically, what do I get here? Take a sample shot and activate. I'm going to make it a bit smaller to fit on the screen. Perfect. So let's activate the first measure. Something like that. And the second measure, 21 milliseconds. So the display is, yeah, it's pretty much in and around 20 milliseconds, controlled by the vertical sync adjustment that you would use to align your picture with the TV. So that baby is working. Fantastic. Let's switch on. I'm just changing the setup here. Switch that off. Let's take the measurements off. Now let's just see if we can find a bit of a square wave now. I'm just going to test point 1. Voila! We have the square wave. That's the frame generator, the frame ramp generator. Test point 1 and test point 2. Ooh, we got a much, let me see if I can slow this down a bit. Much slower one. It's not syncing on my trigger, but yeah, there is a ramp there as well. So these points down here, test point 2 ramp, test point 1 ramp, looking good. All right, just going through, now that we've got the frame sync pulse and the pulse generator working, we've got the ramps. Now looking at the bat controls, and you can see that ramp generator signal is used to good effect in the bat control. If I turn the potentiometer one way or the other, you can see I'm turning it there. I'm getting about a 4-volt drop, depending on where you put it. Oh, I'm gonna ball the balls up, the balls down, and that's working very nicely. So I just gave it a squirt with the Magic Sauce Service-All Super 10. Highly recommended switch cleaner. I really am a big fan of that stuff. You may well have your own preference. This pot is a 22K pot. It probably hasn't had a lot of action for a long time. Made in the UK. Radiome is the company. But the pot's working, and I get a beautiful 4 volts, 4.08 volts. And if we, I might tip this down a bit, I'll show you what I'm doing here. Let's sample the other control, the other resistor. So now we're going to turn this pot, which I haven't sprayed actually. We get the same output, and right to the bottom. Pretty much bang on the same values. So 4 volts, very pleased with that. So the controls are working nicely. You can see a little bit of ripple every time I turn it. There's a little bit of a buzz. If I do it quickly, I need to spray that pot a little bit, but yeah, coming along nicely. Okay, so the validation of this console continues. I'm conscious this video is getting long, but you are seeing the main steps of my debugging, so hopefully this will be of use to somebody. As I was saying, validating now the control and use of the paddles. We know that those are worked. I've sprayed the pots. Tweaking the pots creates a change in position, so of the signal, which is what you'd expect. So on the left and right channel, you take effectively this frame ramp generator and you mix it with the essentially a DC offset from the position controls, and essentially the square wave. Sorry, not the square wave. The ramp wave, the triangle wave, kind of moves up or down a little bit, and reflects the position that you choose on the screen for your things by controlling the pot. That moving ramp wave is then effectively squared through these NOR gates. So at the output here, you have a square wave. And the square wave, the duty cycle on the square wave, so the ratio of how high it is versus how low it is, that duty cycle changes in proportion to your turning. So you've translated the rotation of the pots, which is sort of visually where you want the bats to go up and down on the screen. That has taken a ramp wave and added a DC offset. So as you move the pots and you move the bats up and down, your ramp wave is going up and down. That's going through 2 NOR gates to come out to here, where you get a square wave whose duty cycle varies. So the turning of the pots, the position of the bats, now becomes one about the duty cycle of how long the square wave is on or off. That is then differentiated through an RC network into this NOR gate, and you get some outputs. And I'm trying and show you here on the screen. So if we look at gates, left-hand paddle G16 at pin N4, you now get this sort of square wave, which is a reflection of your position, okay? And that N4, which is the function 5 and 6, if the inputs are 5 and 6, so there's your differentiated signal going into the gate G16. So basically, that differentiated signal there, what you're seeing here, is your square wave with varying duty cycle being differentiated. And then it goes into the gate G16, which is the IC-N4 pin 4 comes out at the output pin 4. Whoops. Just trying to find it up here. Okay. And so you can send that to the composite signal, or you can send the inverse. And to get to the inverse, you should go through N11 pin 4, which is up here. There, I should get the inverse signal, but I don't. I get garbage. Comparing it to the other channel, so let's take a look at N4 or gates G17 and G44. We take this signal, which is your differentiated varying duty cycle square wave from the position controller. So basically that signal there reflects your position. That goes into pin 2 and 3 on gate 17, G17. The output at pin 1 is another square wave. Okay, we just saw one like that for the other controller, the left-hand side. This is the right-hand side. And you can also take the inverse, which goes into gate 44, pin 1, which is up here on this chip. And see, you can see the inverse. And that's not happening with the other bat. In fact, the other bat I'm getting, I don't get the inverse, I get that signal. So that's a problem with chip N11 up here. It's not, for the left and right bats, this chain out here is correct. This chain, this gate G41 is failing. It's not producing the inverse. The reason that you have the output and the inverse is because in these games you can have the bat in a black space, or you can have the white space with a black hole, which is effectively what they call a wall with a hole. And you throw a switch to choose whether you want a bat or a hole. And in this case, the left-hand controller, you'll get the bat, but you won't get the hole. So it looks like N11 has a fault. I'm going to do a bit more checking, but I think I'll have to pull that chip out as well. That out. This is the Pong. I've got one chip working, one paddle working, the other paddle's working. There's a little bit of noise, I'm not quite sure why, and a center line. Not looking too shabby. There's no ball, and I know there's no ball because I found that there's a broken gate on this chip, which prevents the bowl actually appearing. So it doesn't make it to the composite video. I have to repair that. But yeah, so we got the bat, goes up and down. There's a little bit of jitter in it. I'm not quite sure why. It could be, and it seems to like kind of refresh itself. I'm not exactly sure what that refreshing is, but this is a plasma screen up at, I don't know, whatever the frequency is. I have to save it. Cool. Yeah, we're getting there. All right, so I'm trying a few of the other switches here. There's two switches here that can change the gameplay. If I just throw this one, you see what's happening here is it's inverting the bat into a space, and so where the bat's vertical path was, it's filling it in. So it's also adding an oscillation. It's meant to do that. It's meant to give it a wobble, which is a bit tricky. However, I can't believe that's supposed to be the actual speed. It looks a little bit aggressive. So that is that one. So once you throw the switch, you add a little bit of oscillation. Okay. And then if I throw the other switch, I lose this one because, again, there's another broken gate here, which, oh, something was on the screen a minute ago. Where did that go? Which, if I just put that there, again, it's supposed to invert it into a wall with a hole, where the hole is where the bat is. And what did I do there? I did something, and I saw a flash on the screen. I'm not sure. Oh, what was that? Is that the ball trying to appear? I don't know. I saw something then. Anyway, the fact that I've got it this far on a modern TV and it's syncing and it looks pretty cool, it's pretty amazing. So the gameplay would be, and yeah. So the ball isn't being sent to the screen. I know why. As I say, because one of the chips to create the square wave, which shows the position, which is then sent to the screen, blah, 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 isn't working. So now we have some evidence. I mean, I'm going to start to pull the chips off the board and repair them and then compare it with what we've got. Fantastic. Okay, so following the initial test, I was able to fix a few things. One was to replace chip N11 to provide the inverse of the left-hand bat, so the wall with a hole. Chip N10 was replaced to generate the suitable pulse for the ball. The ball didn't appear, unfortunately, and I tracked that down to a fault in this gate here. Pin 10 was giving garbage. So I replaced N5, and what else did I do? Oh, N3 was the historical change that I did to create the frame sync pulsing. So overall, we had 1, 2, 3, 4 chip replacements. Everything else otherwise is vintage, original from 1975, so almost 50 years old. And I will include some video of the working circuit, but this is now back to life as far as I can tell. I'd love to try it with an original CRT TV, so to see if it's a little more smoother in the gameplay. I think with the current television that I have, which is an old plasma screen, it's a little bit finicky, a little bit there's a little bit of blanking, and there's a little bit of I don't know, artifacts on the screen. I don't know. We'll track that down, but functionally the game is working. The ball exists, it touches the bats, it knocks off the top bar and the bottom bar, the serve works, speed controller works, the speed when you hit the ball, the direction of the vertical travel can increase or decrease depending on the speed of the bat. So it's quite a lovely little game to play, all with discrete logic, no software, no ROM. Fantastic. Job well done, I think. So I'll conclude this video with, some videos, some imagery of the gameplay. If you got this far in the video, well, thanks for watching. Thanks for persisting as I tried to troubleshoot this. I'm not that experienced with electronics, and I bought this specifically as a bit of an exercise in learning. And that's what I've done. So, well done. Okay, so just sharing the results of my labor. This is the console connected up to an old plasma screen, and it's kind of in demo mode at the moment. You can see two inverse bats, so the black area is the bats, and they have a bit of a wobble. You see the center line, the ball bouncing around, hitting the top and bottom bar space. It's great. There's a goal. To relaunch the goal, you would push the button, and that reserves, and off you go. You can notice it is dropping out a little bit. There's a little flashing just there. I'm not exactly sure what's causing that. It could be the TV, maybe the output from the sync. Composite sync output is cutting out for some reason. That's something I can take a look at as well. The other modes, if you throw the switches here, see the two switches to connect the different modes. Throw one, and you have a kind of a bat and ball mode. This mode, actually, they call it basketball. If you put the hole at the top, and then you have to hit the ball into the mode. So let's try that. Let's try and get the ball going here. There it is, and oh, too easy. All right, let's try it again. Come on. So I can get this ball to serve. Where are we here? There we go. And yeah, it is fantastic. This thing is working. That dropout is a little bit annoying. Of course, you could have two separate bats, and yeah, it's working. So I'm really pleased. Let's see if I can do a one-handed game. Serve the ball. Come on, serve. Where is it? Oh, it's on this button. There it is. Oh, yeah. Okay, maybe one-handed I can't do it. There you go. Really pleased. Gonna basically, I might try to look at whether the dropout is a problem. I'll probably test it on a different monitor at a different time, and if there's still a dropout, then it's probably in the machine. But there you go. 1975 Pong console. No software, no ROM, just pure discrete logic and a few RC components. And a lot of fun.